Welcome to our AP Precalculus lesson on polynomial functions and complex zeros. In this video, we'll explore some fundamental properties of polynomials that will help us understand their graphs and roots. By the end of this lesson, you will be able to, first, identify zeros and linear factors of a polynomial. Second, use multiplicity to describe how a graph behaves at its zeros. Third, recognize and apply the complex conjugate theorem. And finally, test if a polynomial is an even or odd function. These concepts are essential tools for analyzing and sketching polynomial functions. Let's get started. We'll begin with the relationship between zeros and linear factors. This is the cornerstone of polynomial algebra. Here's the formal definition. If a value a is a zero or root of a polynomial p of x, it means that when you substitute a into the polynomial, the result is 0. In other words, p of a equals 0. So, a 0 is any number that makes the polynomial's value equal to 0. If you were to graph the polynomial, the zeros would be the x values of the x-intercepts. Now the factor theorem connects this idea to linear factors. It states that if a is a real 0, then x minus a is a linear factor of the polynomial. This means you can divide the polynomial by x minus a and the remainder will be 0. It's a powerful tool for factoring polynomials. Let's look at a simple example. Consider the polynomial p of x equals x squared minus 9. We can see that p of 3 equals 3 squared minus 9, which is 9 minus 9, or 0. Since p of 3 is 0, 3 is a 0 of the polynomial. By the factor theorem, we know that x minus 3 must be a factor. And indeed, x squared minus 9 factors into x minus 3 times x plus 3. This connection between zeros and factors is fundamental to working with polynomials. It allows us to build a polynomial if we know its zeros, and to find the zeros if we know the factors. Our next topic is multiplicity and the total number of zeros a polynomial can have. The multiplicity of a zero a is simply how many times the linear factor x minus a appears in the factored form of the polynomial. Think of it as the power of the factor. A factor raised to the power n means its corresponding zero has multiplicity n. This value, n, is crucial because it dictates the graph's behavior at that x-intercept. This leads us to a very important concept, the fundamental theorem of algebra, or more precisely, its consequence for polynomials. A polynomial of degree n, that is, its highest power is n, has exactly and complex zeros, counting multiplicity. This means a fifth-degree polynomial will have 5 zeros. A second-degree polynomial, like a quadratic, will have 2 zeros. These zeros can be real or complex, and if they're real, they can be repeated. Let's use an example to clarify. Consider the polynomial p of x equals x plus 2 times x minus 1 cubed. First, let's find the degree. Here we have a linear factor and a factor raised to the third power. The degree of the polynomial is the sum of the powers of its linear factors, which is 1 plus 3, or 4. Since the degree is 4, we expect exactly 4 zeros. Now let's identify the zeros and their multiplicities. The factor x plus 2 gives us a 0 at x equals negative 2, with a multiplicity of 1. The factor x minus 1 cubed gives us a 0 at x equals 1, with a multiplicity of 3. If we add the multiplicities, we get 1 plus 3, which is 4, matching our degree. This confirms that we've found all the zeros of this polynomial. Understanding multiplicity is crucial not just for counting zeros, but for sketching the graph of a polynomial. That's our next topic. We've established that real zeros are x-intercepts. Now let's see how the multiplicity of those zeros affects the graph's behavior at those intercepts. The rule is quite simple and provides a powerful visual cue. If a real zero has an even multiplicity, the graph will touch the x-axis at that point and turn around. It behaves much like the vertex of a parabola. Conversely, if a real zero has an odd multiplicity, the graph will pass directly through the x-axis at that point. If the multiplicity is 1, it's a straight crossing. If the multiplicity is 3 or greater, the graph will flatten out as it crosses, resembling the graph of x cubed. Let's revisit our example. P of x equals x plus 2 times x minus 1 cubed. We know the zeros are x equals 2 with multiplicity 1 and x equals 1 with multiplicity 3. Let's consider the x-axis. At x equals 2, since the multiplicity is 1, an odd number, we expect the graph to cross the axis. At x equals 1, the multiplicity is 3, which is also an odd number, so we expect the graph to cross again. Because the multiplicity is 3, the graph will flatten as it passes through this point. We also know the end behavior of the graph. The leading term is x to the fourth, a positive even degree, so the graph rises on both the left and right sides. Putting this all together, we can now sketch the graph's general shape. It comes from the left, rises to meet the x-axis at x equals 2, crosses it, and heads towards 1. At x equals 1, it flattens out, crosses the axis, and rises again to the right. This single rule about multiplicity is incredibly powerful for sketching polynomial graphs and understanding their behavior. It's the key to translating algebraic information into a visual representation. So far, we've focused on real zeros, but polynomials can also have complex zeros. This leads us to the complex conjugate theorem. Remember, a complex number has the form a plus bi, where a is the real part and bi is the imaginary part. Its conjugate is a minus bi, where only the sign of the imaginary part is changed. The complex conjugate theorem states that if a plus bi is a zero of a polynomial with real coefficients, then its conjugate, a minus bi, must also be a zero. This means complex zeros never come alone. They always appear in pairs. You can't have a polynomial with real coefficients that has just one complex zero. They must appear in conjugate pairs. Let's demonstrate why this is. Consider a quadratic polynomial with a complex zero, for example, x equals 2 minus 3i. By the theorem, we know that x equals 2 plus 3i must also be a zero. If these are the only zeros, we can reconstruct the polynomial from its factors. The factors are x minus the first zero and x minus the second zero. So we have x minus 2 minus 3i times x minus 2 plus 3i. Let's multiply this out. We can group the terms as x a 2 and the imaginary part. This looks like a difference of squares, a plus b, a, b. This simplifies to x minus 2 squared minus 3i squared. Expanding that gives us x squared minus 4x plus 4 minus 9i squared. Since I squared equals -1, this becomes x squared minus 4x plus 4 plus 9, which is x squared minus 4x plus 13. And look at the result. The polynomial x squared minus 4x plus 13 has real coefficients. There are no imaginary terms. This illustrates why the theorem must be true. Complex zeros must come in conjugate pairs to cancel out their imaginary parts and form a polynomial with real coefficients. It's a beautiful example of how complex numbers maintain consistency within our number system. Next up is a concept that connects a polynomial's degree to patterns in its sequence of values, successive differences. Imagine a table of values for a polynomial function. We can find a relationship between the x values and the polynomial's degree by looking at the differences between the y values. For a linear function which has a degree of 1, the first differences of the y values are constant. If you find the difference between consecutive y values, the result is always the same number. For a quadratic function, with a degree of 2, the first differences are not constant, but the second differences are. You take the differences of the first differences, and that new list of numbers will be constant. This pattern holds for all polynomials. A polynomial of degree n will have constant nth differences. This method is incredibly useful. If you are given a sequence of numbers, you can determine if it is modeled by a polynomial function, and if so, its degree. Let's work through an example. Here's a sequence of numbers: 1, 6, 15, 28, 45. Let's find the first differences. We subtract each term from the next one. 6 minus 1 is 5. 15 minus 6 is 9. 28 minus 15 is 13. And 45 minus 28 is 17. The first differences are 5, 9, 13, 17. This is not a constant sequence, so the original sequence is not linear. Since the first differences weren't constant, let's find the second differences. We do the same process with our new sequence. 9 minus 5 is 4. 13 minus 9 is 4, and 17 minus 13 is 4. The second differences are constant. This tells us that the original sequence can be modeled by a quadratic polynomial, which has a degree of 2. So just by doing some simple subtraction, we can identify the type of polynomial involved. This is a very elegant way to connect the arithmetic of a sequence to the algebra of its generating function. Our final topic is about the symmetry of polynomial functions. We classify polynomials as even or odd based on how they behave when we replace x with negative x. An even function is one where substituting negative x into the function yields the exact same function back. In other words, f of negative x equals f of x. Geometrically, this means the graph is symmetric with respect to the y-axis, like a parabola. An odd function is one where substituting negative x gives you the negative of the original function. That is, f of negative x equals negative f of x. Geometrically, the graph is symmetric with respect to the origin, which means if you rotate the graph 180 degrees around the origin, it looks the same. An important side note for polynomials. An even polynomial contains only even powers of x, like x squared, x to the fourth, and constant terms. An odd polynomial contains only odd powers of x, like x, x cubed, and x to the fifth. A polynomial with both even and odd powers is neither even nor odd. Let's test an example. F of x equals x to the fifth plus 2x cubed. It only has odd powers of x. To determine if it's even or odd, we calculate f of negative x. F of negative x equals negative x to the fifth plus 2 times negative x cubed. An odd power of a negative number is negative, so this simplifies to negative x to the fifth minus 2x cubed. Notice that we can factor out a negative 1 from this expression. This gives us negative times the quantity x to the fifth plus 2x cubed. And the expression in the parentheses is just our original function, f of x. Since f of negative x equals negative f of x, we can conclude that the function f of x is an odd function. This test gives us another piece of information that helps us quickly understand and sketch the graph of a polynomial by knowing its symmetry. Let's quickly summarize what we've learned today. We've covered several powerful tools for analyzing polynomial functions. First, we learned that zeros are the values a that make p of a equal to 0. Second, the total number of zeros a polynomial has is determined by its degree. A degree n polynomial has exactly n zeros. Third, we saw that the multiplicity of a real zero dictates the graph's behavior. Even multiplicity means the graph touches the x-axis, while odd multiplicity means it crosses the x-axis for odd multiplicity. Fourth, complex zeros always come in conjugate pairs, a plus b and a minus bi, for polynomials with real coefficients. Fifth, successive differences allow us to determine the degree of a polynomial, with the nth differences being constant for a degree in polynomial. And finally, we learn to test for symmetry. Even functions are symmetric about the y-axis, while odd functions are symmetric about the origin. And odd functions are symmetric about the origin. Mastering these concepts will greatly enhance your ability to understand, analyze, and sketch polynomial functions in AP Precalculus. Thank you for watching.